Okay, welcome to the second video on linear algebra with Python and NumPy. And the first thing we're going to do is actually leave NumPy behind for a second. Oftentimes, you're going to want to do row reduction or Gaussian elimination in order to solve some system of equations. So say, I'm going to scroll way up to the top here. Say I wanted to solve a times some vector equals u. Okay, so say that's what I wanted to do. Well, I can do that by augmenting a and u together and row reducing, right? So I'm going to start off by printing a and printing u, just so I know what vectors and matrices I'm dealing with here. And so normally on paper, I would just row reduce this, and NumPy does not have a row reduction scheme. That's exactly right. NumPy does not have row reduction. Okay, this is something to keep in mind, but there's a really good reason for this. Row reduction is a really slow process. NumPy is designed to do linear algebra super fast. Well, at least the NumPy linear algebra stuff is linear algebra really fast. Row reduction doesn't fit into that scheme, but symbolic Python does have that. So I'm going to import SymPy as SP, not NP, because this is symbolic, not numerical. And now things are going to change just slightly, but the ideas are still the same. So I'm going to say A is, actually I'll say AU is equal to sp.matrix with a capital M. Why they changed the case, I don't know. It's still a list of it lists. So 1, 2, 3, 3, because I'm going to augment this thing by hand. So 4, 5, 6, 4. And then 7, 8, 0, minus 1. Okay, so I print the darn thing. It doesn't even print it in a nice way because symbolic Python basically hates us. I'm kidding a little bit, but symbolic Python is not amazing in all the things that it does. But it does row reduce, so check this out. AU dot, it knows that this is a symbolic thing. Now there's all sorts of things that I can do to this symbolic matrix. And one of them, I could find the determinant if it was square, which it's not. I could get the reduced row echelon form and fire it away, and it gives me the reduced row echelon form. Or does it? Oh, that's what I wanted. Okay. Sorry about that. I forgot open close parentheses on the reduce row echelon form. Here, let's just take the print command off of there. There we go. I just want the reduce row echelon form. So it actually reduces to an identity matrix, and then -5/3, 4/3, 2/3. So this would be the vector that if I multiply a times that vector, I will get the vector u. Okay, so that's all well and good. We can do row reduction. But NumPy does linear solves really fast. So let's go back to NumPy. I don't need to import it again, but let's just say we had to, okay? I've got the matrix A, I've got the vector u, and let's say we want to solve ax equals u. Okay, so I want to get the vector x. Well, what I'm going to do is say x is equal to np.linalg, linear algebra.solve. And if I do this in just open close parentheses, it tells me I'm solving the linear matrix equation ax equals b, where the a in my case is capital A, and the b in my case is the vector u. Oops, I printed u. I should print x. There we go. And there we are. -5/3 is what symbolic Python gave us. Numerical Python gives us -5/3. 4/3 is what we got from symbolic Python. 4/3. 2/3, 2/3. So I encourage you, if you're solving a linear system where you don't actually have to have the steps of row reduction in front of you, to actually use NumPy and solve the system ax equals u with linalg.solve, np.linalg.solve. Right? So it's a really nice, handy little tool. Now, if I did this with B, we know that B was a singular matrix, the one that we defined way up above, and it will error out and tell us that we actually have a singular matrix. So it's not going to work, obviously, for a singular matrix. Okay, I'm going to stop this video here, and I'm going to do the rest of what's in this notebook in the third video.